Greetings everyone, this is Mr. Mull. Today I'm doing a podcast on how to draw Lewis dot diagrams for compounds that are ionic. So first we're going to start off by recapping what ionic compounds are. Ionic compounds, when we see them, we're going to be noticing the types of elements involved. And when we notice those, we're going to notice that they always start with the metal. Strontium, rubidium, aluminum, gallium. And they're going to be paired up with a nonmetal. Fluorine, oxygen, bromine, oxygen. So when I have metals and nonmetals bonding together, we're talking about an ionic bond. So when I have these ionic bonds, metals have a really low electronegativity. They have a really low tendency to hog electrons. So because they have a low electron hogging tendency, they're going to readily lose those electrons. And they're not just going to lose any random number, they're going to lose electrons until they completely empty their outermost valence electron shell. Nonmetals are kind of the opposite. They have really high electronegativity values, so they're looking to gain electrons until they fill their highest or their outermost valence shell. And remember, when we're talking about valence shell, our valence electrons, we're talking about the highest energy level S and P electrons. Okay, that's what we're talking about. So we're filling that outermost energy level, or we're emptying it. And when I have these really electronegative atoms, such as oxygen, electronegativity 3.5, with a low electronegativity atom, such as rubidium, electronegativity 0.9, what happens is those electrons are completely transferred. When we have this very big difference in electronegativity, and we're talking about, usually that difference is greater than or equal to 1.7. When that change in difference in electronegativity, we're talking about ionic bonds. Now, it's not always going to be a perfect around 1.7 or bigger than, but it's a general rule of thumb. It's a metal and a nonmetal, and it has a high difference in electronegativity. We're going to have an ionic bond. So when we get to our filling our valence shell, okay, we're trying to get to the magic number, 8 electrons in the outermost level. Highest S and P are going to get 8. And remember, that first energy level can only hold 2. But 8 is usually the magic number. So we're going to go ahead and look at how these electrons are going to show up around our atom. So in a Lewis dot diagram, there is 4 regions for electrons. And in these 4 regions, we can fill our 8 electrons. Now the one up top is going to be the place that we're going to put our S electrons. And then the other 3 are going to be our P orbital electrons. And there's going to be 3 of those. Remember, there's 6 electrons in a P. There's 3 different orbitals. So you can think of these as different orbitals. So as I'm filling up, there's my 8 electrons. And we always fill the S first. You can put some little dots in there. And then Hund's rule says we have to fill 1 in each first. And then we could just keep filling from there. Okay, so this is how we're going to fill these up. So when I'm looking at a problem, we're going to draw a Lewis dot diagram for a compound now. This is strontium fluoride. We're going to try to figure out what kind of bonds this forms and then where the electrons are going. And we're going to show those with dots. So before I start out, I'm going to kind of draw this central atom here, strontium. The metal is always listed first. I'm going to go ahead and draw strontium and put an F on each side. Kind of make strontium kind of a central atom. And I'm going to figure out how many electrons do each of these atoms have in their valence energy level. So I could go through for each of these and figure out the electron configuration, and I could figure out the highest energy level S and P electrons, and I could add them up. You know, strontium, for example, is in the 5th energy level. It has 2 electrons in the S, so it has 2 valence electrons. Fluorine is in the 2nd energy level. It has 2 in the S and 5 in the P, and I could add those up and I could get 7. A really fast way to find the valence number of electrons is to just look at the old school group number notation. So strontium is in group 2A, fluorine is in group 7A. So if we look at those numbers, for the old school group number notation, it's actually going to be the number of valence electrons and those highest S&P electrons. So strontium does in fact have 2 valence electrons, and fluorine has 7. So you can always look at the group number as kind of a quick way to count up those valence electrons. Okay, so we're going to say group number, okay, old school group number. Okay, so those Roman numerals. So strontium has 2 electrons. I'm going to put those in the S. And fluorine has 7. So I'm just going to put a little X on here so I can distinguish between my dots, but you would just use a circle, that's fine. 1, 2, 3, 4, 5, 6, 7. Hund's rule is taking place how I'm drawing these. Fluorine has 2 in the S and 1, 2, 3, 4, 5 in the P. Okay, so here's fluorine. So strontium wants to get rid of its electron. Fluorine wants to gain one. So this is kind of a mutually beneficial arrangement. Strontium is going to go ahead and find 2 fluorines to give its 2 electrons to, so that fluorine can now get 8 and it can have a full inner shell. So strontium is going to come in, and metals are going to do what with their valence electrons? They're going to lose them. So this electron is going to go over here, and this other fluorine is going to take this other one. And so now I'm going to go ahead and move those around, and I'm going to draw what we have left over. I have a strontium. I'm going to draw a bracket here. This is the notation, the way we're going to do this. So the strontium is now, its valence electron level that it used to have is now empty. So even though it has inner electrons, I'm going to leave that outermost empty, and I'm not going to put any dots in here. And because I've lost 2 electrons, but I have the same number of protons, I gain that charge of plus 2. And I'm going to draw my fluorine, and I have fluorine. Fluorine has now gained an extra electron. So fluorine used to have 1, 2, 7. Okay, I'm just going to draw some little dots on there. But it has gained 1 electron. I'm just drawing it as an X so that you can really clearly see that it's something it didn't have before. And so now it's gained 1 electron, and I have 2 of those fluorine. So I'm going to put a coefficient out in front of that bracket. So this is my overall, we're going to call this a Lewis dot rep. Okay, a Lewis dot representation. So this is going to show me the Lewis dot rep for strontium fluoride. So my metals got rid of my outermost electron, and my nonmetals gained an electron, and it gained 1 electron, so it has to have a minus 1 charge. So there's all the pieces together, minus 1 charge. We're avoiding, so I'm going to draw what not to do, we're avoiding something like this, where strontium, you may have seen this in some of your other classes, is kind of like in the center, and it still has its electrons around it, and fluorine is around here. This is an incorrect way of notating this, because strontium does not have those electrons around. Those electrons have been removed from it, so this is not going to show that. This is the correct way to show this. I'm going to go ahead and do another example here. This one to the right would be implying that they were sharing electrons, which is not the case. We're going to do another example, rubidium. So I'm going to do the same idea here. I'm going to look up rubidium. Rubidium is in group number 1, okay, 1A. Oxygen is in group 6A. So that tells me that rubidium has 1 valence electron, and oxygen is going to have 6 valence electrons. So I'm going to go ahead and draw, I'm going to draw oxygen in the center this time. I'm going to draw my rubidium on each side. And oxygen has 6 valence electrons, so I'm going to draw 1, 2, 3, 4, 5, 6. And rubidium has 1 electron each. So I'm going to go ahead and draw rubidium's 1 electron in the S. So what's going to happen is oxygen is going to be looking for electrons to fill its outer shell. Rubidium has 1. It wants to empty its outer shell out. So those electrons are going to transfer because oxygen's electronegativity is so high and rubidium's is so low. This is going to take place. I could find the difference between those, and they're going to be much greater than 1.7. So oxygen is a nonmetal. It has 6 electrons. It needs 2 more. has 8 total electrons. It needs 2 more to fill out that outer energy level. So it gets to 2, and when this happens, now I'm going to draw my metal first. Rubidium is out of electrons. It has gained a charge. Now it's +1, and I have 2 of them. And then oxygen, I'm going to draw that in a bracket, now has 2 extra electrons. And I'm just going to draw an X. And oxygen now has a -2 charge. Something I didn't show you last time, I want to show you on this one, is that because this compound originally was neutral, okay, there's no like floating charge up here, that means that the charges have to be conserved. So if I go back and I do 2 times +1, okay, it's going to be +2. And then I have 1 oxygen here, and I have a -2 charge, -2. It's always going to add up to 0. So we need to have my charge conserved. And that will be the case. So here's my final answer for the Lewis dot rep. Let's go ahead and do one more. Aluminum bromide, we're going to go ahead and look through, and maybe you can find a trend. Okay, aluminum is in group 3, 3A. Bromine is in group 7, VIIA. And so what's going to happen is aluminum is going to have 3 electrons. It is going to lose. Bromine has 7 and wants to gain 1. So we have 3 of them. Okay. The group number is going to be a good clue for metals at what charge they're going to form and how many electrons they're going to lose. So aluminum has 3 electrons, 2 in the S, 1 in the P. It's going to clear out that outer energy level, and it's going to be left with nothing in there. And when it gives up those 3 electrons, it's going to get a +3 charge. And I have my 3 bromines. And those bromines are each going to take on an electron. Okay, so we're going to get those. Okay. We're going to, oh, excuse me, they only took on 1 electron each. Okay, so those should just be circles. So we'll just make one of those an X. Each one of those bromines only could get 1 more. So what happens is, if we wanted to check our charge, I have 1 aluminum plus 3. I have 3 bromines, which are -1. And it's going to be conserved. Okay, so this is going to be our Lewis dot rep. And we could go through and do some other examples. And the same idea here. Gallium is in group 3A, so it's going to form group 3A. Oxygen is in group 6A. So gallium is going to likely form a +3 charge, just like aluminum. Oxygen, we have 3 of them, 2 of these. It's going to form a -2 charge. It needs 2 more electrons to fill its outer energy level. Okay, so I'm going to draw my oxygen. I do need to draw dots on oxygen because it has a full outer energy level. So we need to draw those dots, -2. I could check the charge. 2 times 3 is +6, minus 3 times -2. It's going to give me 0. Charge is going to be conserved. And they're always going to pair up in this ratio. Okay, they're always going to pair up in this ratio so that everybody is happy. All my gallium have lost their electrons. The 2 gallium have lost those total electrons, and my oxygen have gained them all. So everyone is now happy. In summary, my metals are always going to empty out. Okay, they're going to empty out so that we have...
John Paul Trezano, please bring Chris's dollar back. John Paul, thank you.
We're going to empty out our outer shell, and our charge, okay, empty, and then our charge is going to be how many we empty. Okay. Charge is going to equal number of electrons lost. For our nonmetals, we're going to be gaining to fill our energy level, to fill, and we're always going to have a charge equal to the number of electrons gained. I'd like you to do from the worksheet the questions that deal with ionic compounds, and I hope that this was helpful.